Okay, so we're going to be talking about tangential and normal components of acceleration and how we can utilize and exploit the tangent and normal directions of a dynamics problem to better understand the equations of motion for a given system. If we have an idea of the path of a vehicle or object, it is often convenient to analyze the motion using tangent and normal components, sometimes called path coordinates. So tangent would be tangent to the path here, and normal would be normal to the path. And we'll see that even more clearly on the next slide. Okay, so here we have the tangent and normal directions, and v, our velocity, is going to be equal to the speed times the unit normal in the tangent direction. So that's a key concept to understand. Our velocity only has a component in the tangential direction. So our velocity equals the speed times the unit normal in the tangent direction, whereas the acceleration will be the derivative of the speed times t. And by the way, this curved v, I'm going to call that nu, in u. It's a Greek letter, and this is rho. This italicized looking p, that will be rho, and this will be nu. And these are key things to understand. I'll circle them real quick. This one and this one. Moving forward to solve the problems, these are two key concepts. Rho is going to be the instantaneous radius of curvature, and this nu is going to be the equivalent of speed. And so if we break down acceleration, it's going to be d nu dt in the tangential direction, and then in the normal direction, it is our speed squared over rho. And that is a key thing to remember as well. So I'll read these real quick. The tangential direction is tangent to the path of the particle. This velocity vector of a particle is in this direction. So the velocity vector of the particle is in the tangential direction. The normal direction is perpendicular to that tangent direction, and it points towards inside the curve. The acceleration will have components in both the normal and the tangent direction. So to derive the acceleration vector in tangential and normal components, define. So first, kind of how this presentation is going to be broken down is we're going to do some derivations, which sometimes can be a little bit cluttered and confusing, but when we get to the problems, hopefully it will make more sense. So hang in there through the derivations if it seems a little bit confusing and you bring back a lot of things from calculus, all of this stuff here. But I'll still explain it. Here we have 2 points, P and P prime. P prime is just you could consider it like an instant, 1 instant after, and so it travels that far. We can break it into our tangent and our normal directions here. And if we want to basically derive a formula for calculating the normal direction, you could use this here, which would be after just an instant later, as we move delta et, so delta e sub t, we go 1 instant, and then we'll call this delta theta. So delta et equals 2 sine delta theta over 2. And the limit of delta e sub t over delta theta as it goes to 0, that's eventually going to equal this, the component, the unit normal in the normal direction. So essentially what this all points to here is to calculate the unit normal vector. It would just be the derivative of the tangential vector with respect to theta. this being theta here. So now we'll get it even a little more convoluted on this slide, but as convoluted as these derivations can be, the final thing used for solving problems, which is right here, if we kind of work backwards from that, it feels more intuitive to me. So our acceleration equals the derivative of speed with respect to time for the tangential component, and in the normal direction, this might not feel intuitive, but it can be memorized, and it almost is a little bit intuitive as we work through a few problems. The acceleration, if you imagine this particle moving, the acceleration in the normal direction is the speed squared divided by the instantaneous radius of curvature, or rho. So we can see that it's just written in the two components here. We're going to have a problem where I'm sure that we'll solve the acceleration of some system for the tangent in the normal directions. But to quickly go through the derivation of how we get that, A equals, this is day one of dynamics, acceleration is the derivative of velocity. So we can say the derivative of speed with respect to time in the tangential direction plus speed times dE dt. And that would further equal dV over dt in the tangential direction. And we can break this to dE d theta ds, ds dt. And S is our arc length. So delta S is the arc length here. Delta theta equals delta S over rho. So this is already finalized. We want to get, this is going to be the normal direction here. And in order to get to that point, we can say that the unit normal direction is the derivative of the tangential direction of, with respect to theta, we got this on the last slide, times, and I'll switch to laser pointer here so I don't clog it up too much, rho d theta equals ds. So ds over dt equals the speed. So this ds dt is right here. That's going to be nu. So if we plug that nu in right here, that would be nu squared, right? That's speed squared. And then dE with respect to d theta, if we put the d theta on this side, we can turn this into a rho somehow. I'm not seeing it yet. D theta equals E sub, oh, so this gives us, this dE d theta gives us the normal direction. That's how we get our normal direction. And then d theta over ds, that gives us the rho. Okay. So the final product of this complex derivation is this formula right here, which the formula to me seems more intuitive than the derivation. And let me read these two statements. The tangential component of acceleration reflects change of speed, and the normal component reflects change of direction. The tangential component may be positive or negative. The normal component will always point towards the center of the path. So we could be accelerating or decelerating, but if we are turning in this direction, our normal component of acceleration will always be towards the inside of the curve. It won't be towards the outside. Whichever direction we're turning, that is the direction which we are accelerating. So this derivation is not as complex. Now we're just going to expand to three-dimensional components very quickly. Relations for tangential and normal acceleration also apply for a particle moving along a space curve. So let's say we're not in two dimensions anymore. We're going to expand to the x, y, z coordinates. We have a e sub t and a e sub n, our tangential component, our normal component, and then we add this new one, e sub b, which is just going to be the cross product of e sub t and e sub n, and it's just going to be referred to as the binormal of the two. So we still have this equation here, acceleration in the tangential and the normal. We don't even have an acceleration component in the binormal, so that is good. All the acceleration occurs in the oscillating plane, and the oscillating plane can be instantaneously calculated for each individual moment. So the plane containing the tangential and normal unit vectors is called the oscillating plane. The normal to the oscillating plane is found from simple vector mechanics here. The cross product of e sub t and e sub n gives us e sub b, the binormal. E sub n is the principal normal, and e sub b is the binormal, because we already have a normal, so the normal to the normal and tangent, we'll just call it the binormal. And I don't know how many problems you'll see that involve 3 dimensions, but it'll most likely be about a certain moment, so you'll be able to simplify it to 2 dimensions. Acceleration has no component along the binormal, so that's why this derivation is not as complex. Luckily, there's no component in the binormal direction, so we can keep that pretty simplified. So now let's do a sample problem and try to understand the sample problem very well, and that should give a good understanding of this method of solving dynamic problems. So let's read it very quickly, and I'll just pull all these up. I think that's it. A motorist is traveling on a curved section of highway of radius equals 2,500 feet. So if you're doing this on a sheet of paper or something, that would probably be beneficial, and just see if you can solve it using the equation from earlier. You should be able to solve it with the equation derived on the previous slide. The speed is 60, so that's nu, in u, a Greek letter. It's like a V, not an R, sorry. Equals 60, and that's in the beginning. And then V2, nu2, equals 45. And then T is going to equal 8. And sorry, I was just skipping ahead and writing all the numbers down. Normally I do that when I solve these problems. I just get all my numbers written down and then see how to solve these things. So the instantaneous radius of curvature for this section of highway, probably an off-ramp of a highway, is 2,500 feet. And the instantaneous speed is 60 miles per hour. The motorist suddenly applies the brakes, causing a deceleration of the vehicle, causing the automobile to slow down at a constant rate. Knowing that after 8 seconds the speed has been reduced to 45 miles per hour, determine the acceleration of the automobile immediately after the brakes have been applied. So we're doing this about the moment right here, not further down the road when we're traveling 45 miles an hour. We want to know the instantaneous acceleration using that formula from a few pages ago, which I'm pretty sure was speed in the tangential direction, and then speed squared over rho in the normal direction. So it's not a lot of components. With using these two, we should be able to solve it. So let's go to the next slide and see if that's how they do it. So first, they convert it from miles per hour to feet per second. Okay, that's fine. 60 miles per hour, 5,280 feet per mile, 1 hour, 3,600 seconds. Make sure you don't make any simple mistakes by flipping these the wrong way. Always do a sanity check. Make sure it's not like 8 billion feet per second, but it's pretty simple to do if you take your time and make sure these things cancel out. Like miles cancels out here, hours cancels out here, and then feet per second. So we do that. We get 88 feet per second and 66 feet per second. So first we want to calculate the acceleration in the tangential direction. So how do we calculate the acceleration in the tangential direction? We know that we started at 88 feet per second, and then when we get down there, we are going 66 feet per second. So we start going 88 feet per second, and then over here we're going 66 feet per second. Let me switch back to laser pointer. So here 88, here 66. So 88 minus 66 over 8. They did it backwards. For me personally, I think I would have just... It makes sense that they're doing it backwards because that's how they get a negative number. For me, I think I would have just wrote 88 minus 66 over 8, and then I would just know that our acceleration is in the negative direction because we are decelerating. We're not accelerating, we're decelerating. So that's how it makes sense in my brain, but this ends up being the same too. So 66 minus 88 over 8, our tangential acceleration is going to be negative 2.75 feet per second squared. Immediately after the brakes are applied, the speed is still 88 feet per second. So now we can do that equation for the normal. The reason that we did this is to get the tangential acceleration. Now we need the normal acceleration as well to get the full acceleration, and that'll be Pythagorean theorem here. But let's just stay right here for now. That's going to be speed squared over rho. Speed squared is 88 feet per second squared. We're going to square that and divide it by 2,500 feet. So our acceleration in the normal component is 3.1 feet per second squared. Next, we can do Pythagorean theorem and square both of those and take the square root of that to get the full acceleration, the total acceleration. And that's going to be in this direction. It helps to draw these out to get a good understanding of where it is, because we know that we're decelerating, so we know that our tangential component of acceleration is in the negative direction here, and the normal component of acceleration is going to be towards the center of the curvature there, and just the combination of the two, Pythagorean theorem, however you want to look at it, it's in this direction here, and that's going to be 4.14 feet per second squared. You square it so there's no negatives, the negative doesn't matter. And then to get acceleration, you just do the tangent of this alpha angle here is going to be, this over that, a sub n over a sub t. So tangent of alpha equals a sub n over a sub t. And if you have your TI-83 or whatever calculator you're using, you could just do inverse tan of this number here. You do the inverse tan of whatever this is, and that's going to give you this angle here. If your calculator's in degree mode or whatever, so that's not too complicated. I think that this part is pretty intuitive here, getting the normal component of acceleration, because you're basically given that information. You're given the velocity at that moment, and you're given the radius of curvature, the instantaneous radius of curvature. This might be a little complicated, but after seeing the problem, hopefully it makes a little bit more sense. So that's how you calculate your tangential acceleration. Other problems might have little twists and stuff like that, and that's just part of the challenge of dynamics, is just trying to do as many problems as you can and get a good grasp of the concept, and hopefully be able to do the problem when the test comes, because it's not going to be too much different from the problems that you see in the book. It'll be similar to those problems. So you just want to get a good intuitive understanding of this, and that's how you learn dynamics, essentially. So now we're going to reflect and think on it, okay? The tangential component of acceleration is opposite the direction of motion. That makes sense because we are decelerating. So, of course, if you're stepping on the gas here, then it's going to be in the direction that you're going. Your acceleration would be in that direction, but we're decelerating, we're hitting the brakes, so it's in that direction. That's pretty simple to understand. And the normal component of acceleration points towards the center of curvature, this way. So again, not too complicated to understand, which is what you would expect for slowing down on a curved path. Attempting to do this problem in Cartesian coordinates is quite difficult. And that's another good point. A big part of dynamics is picking the correct way to solve the problem. You got to learn all of these different methods and then be able to apply the correct method to the problem, and it'll make the problem easier. Like if this was in Cartesian coordinates and you had these sine thetas and cosine thetas, it can get very complicated. Whereas using this method, you get that nu squared, speed squared over rho, and that it will simplify certain things. Okay, so continuing forward with tangential and normal components. In 2001, a race scheduled at Texas Motor Speedway was canceled because the normal accelerations were too high and caused some drivers to experience excessive G-loads, similar to fighter pilots, and possibly pass out. What are some things that could be done to solve this problem? I'm not sure. I mean, I guess all you could do is go slower. Let's see what the answers are. Some possibilities. Reduce the allowed speed. So that's kind of an obvious one. Increase the turn radius. So that makes sense. If you increase the turn radius, your g-force isn't going to be as much, because I'll just write down that normal component of acceleration again, even though you probably already have it written down. If your turn is wider than rho, right here, your instantaneous radius of curvature will be higher. So this number in total, because it's on the bottom part of that fraction, it's going to be smaller. So increasing the turn radius, and that's kind of intuitive as well, but just so we see it in the equation, increasing the turn radius would certainly decrease the normal component of acceleration. And then the third solution, I guess, they provide is have racers wear G-suits. I don't know what that is, but I guess that would probably help too. Maybe it's like an astronaut suit or something. So here we have another problem. It looks like this one is going to be basically a little capsule that spins around on this stick. I think it's something that astronauts use to test out how much G-force they can handle. The tangential acceleration of the centrifuge cab is given by a sub t equals 0.5 t, where t is in seconds and a sub t is in meters per second squared. If the centrifuge starts from rest, determine the total acceleration magnitude of the cab after 10 seconds. Okay, so we want our total acceleration, but we're only given the acceleration in the tangential direction. So we need to calculate that formula for the strategy, right? Define your coordinate system, calculate the tangential velocity and tangential acceleration, calculate the normal acceleration, determine the overall acceleration and magnitude. So for this one, calculate the tangential velocity and tangential acceleration. This is the tangential acceleration, so that'll be easy. But tangential velocity will be difficult. And that's we're gonna have to use an integral, I believe, because A equals dv dt so therefore V equals the integral of A with respect to t, right? So we'll have to integrate that from 10 to 0, and we'll see that on the next page. We'll have to calculate the normal acceleration. That's not too bad because we know that formula. Once we have this velocity term, mu, or speed, I've written that down a few times now. The normal acceleration equals nu squared over rho. So no problem there. And then determine the overall acceleration. That's Pythagorean theorem. So let's get going with that. Right off the bat, we see a mistake, I think, because that's a 5, and that's an 8. So something is off. I guess if you solve this problem, well, I don't know if they solve it for 5 or 8, so we'll just have to look at it. A sub t equals 0.5 t. Well, we do the integral here. Integrate it from t to 0, 0.5 t dt. You take the integral of that. You get t squared. You divided that 5 by 2. So 0.25 t squared. 0.25 t squared. And then we have to do that from t to 0, so that's going to be a 10, right? So yeah, 0.25 times 10 squared, you get 25 meters per second. That's the instantaneous velocity, which is all in the tangential direction, because our velocity only has a component in the tangential direction. Our velocity does not have a component in the normal direction. That's a key concept to understand. The velocity only has a component in the tangential direction. So now we'll determine the normal acceleration using that tangential velocity or speed squared. 25 squared over 8. Looks like they used the 8. And that's going to give them 78.125 meters per second squared. Determine total acceleration and magnitude. So how are we going to do that? We need our tangential acceleration, 0.5 t, which is 10, so that's going to be 5. So 78.125 squared plus 10 squared, square root of that. Boom. Total magnitude is a sub n squared plus a sub t squared, which is all of that right there, 78.125 squared, plus, I said 10 squared, sorry, it's 5 squared. 0.5 times 10 is 5, so 5 squared. And you get this as your answer. Direction, I guess they don't ask for direction, because we don't really know. I guess it doesn't matter. Now we can reflect and think on it. Notice that the normal acceleration is much higher than the tangential acceleration. What would happen if, for a given tangential velocity and acceleration, the arm radius was doubled? So we have a given velocity. Okay, so let's see. What would happen if, for a given tangential velocity and acceleration, the arm radius was doubled? So we went from 5 to 10 meters, but our velocity stays the same. Well, I'll write this same formula that I've written down one more time. Obviously, it's a very important formula. A sub n equals mu squared, speed squared, over rho. If 5 is doubled, basically we know our normal acceleration is going to go down. If this number on the bottom gets bigger, this number gets smaller. If this number on the bottom of this fraction, and this number stays the same, and this number gets bigger, this number will get smaller. Pretty sure. Well, I mean, that's obvious. I'm just making sure that it's that my logic is correct. So what would happen if for a given tangential velocity and acceleration the arm radius was doubled? The normal acceleration would go down, and the tangential velocity would and acceleration would remain the same, because it's literally in the question. What would happen for a given tangential velocity and acceleration? So tangential acceleration should stay the same. So we know it's not B. The accelerations would remain the same. No. The a sub n would increase and a sub t would decrease. No. The a sub n and a sub t would both increase. No. The a sub n would decrease. Yes, it would decrease because of what I just explained here. So let's see if that's correct. That is correct. The a sub n would decrease, and that makes sense. If you double the length of that radius of the arm there, the normal acceleration is going to be smaller. If you're in this and it's spinning around at a given rate, the longer that arm is, the lower that normal acceleration would be. So you can think about that for a little bit if you need to. It is kind of it's a little bit wordy, but it does make sense. So now we're going to talk about the radial and transverse components. In the radial and transverse components, we're not making a big jump into something totally different from what we're doing. You will quickly learn that the radial and transverse components are very similar to the ones we just did, which was tangential and normal directions. The radial and transverse components are quite similar to those. So the foot pedal on an elliptical machine rotates about and extends from a central pivot point. This motion can be analyzed using radial and transverse components. Fire truck ladders are another one. Can rotate as well as extend. So when something can extend in the radial direction, that's when you kind of want to be thinking in terms of radial and transverse components. The motion of the end of the ladder could be analyzed using radial and transverse components. So here we have radial and transverse components on a free body diagram. You can see it looks almost the same. I guess that you could, if you were going to switch this to tangential and normal directions, just to quickly do that, and then I'll get into what this is. This would be tangential, and this would be normal. E sub t and E sub n. But for this case, if it was circular, they'll even line up to the point where the normal would be opposite if this was a perfect circle. And I think we're going to see an example of that. So let me clear that clutter out of here. and now explain this very clearly. So the position of particle P is expressed as a distance r from the origin O to P. This defines the radial direction E sub r. The transverse direction E sub q is perpendicular to E sub r. So E sub q would be the direct opposite of E sub r. You'll have to remember that. I don't think you use that on too many problems, but there's a question later in the slides that uses E sub q for some reason. But so the transverse direction E sub q is perpendicular to E sub r. So E sub q is actually in this direction. I guess this would be E sub q in that direction. But anyway, the r vector, this is a position vector, is r times E sub r. That's this in blue. E sub r is a unit vector. The italicized r is a scalar quantity. So r equals the position r equals just the scalar quantity multiplied by that unit vector. That isn't complicated to understand. It does get complicated as we move forward to these ones, though. And there will be a derivation which is even more hectic than the previous derivation, but the final formulas are written right here, and the final formulas will be the ones that you utilize to solve problems. The particle velocity vector is velocity equals r dot times E sub r plus r theta dot times E sub theta. The particle acceleration vector is acceleration equals r double dot minus r theta dot squared, and that's the radial component of that, plus r theta double dot plus 2 r dot theta dot, and that is the theta component of acceleration. So still think of it in terms of components, because that's most likely how questions will be organized. And let's go into the derivation of this. So we can derive the velocity and acceleration relationships by organizing that the unit vectors change direction. Here we have the position vector. The derivative of the E sub r with respect to d theta equals E theta, and the derivative of E theta with respect to theta equals negative ER, so that would be in this direction. d E sub r dt equals d E sub r d theta times d theta dt equals E theta times d theta dt. So the derivative of, we're kind of taking this d E sub r dt and getting to E theta d theta dt with this equation. And then we have d E theta dt equals d E theta d theta multiplied by d theta dt equals the negative E sub r d theta dt. And these are a little bit complicated, but we'll use them for the next set of equations here. The particle velocity vector, this gets a little more simple here. What this is here is the derivative of position. Velocity equals the derivative of position. So if we're going to take the derivative of r multiplied by E sub r, we have to use a product rule here. We have to take the derivative of r and then the derivative of, and multiply that by E sub r, and then the derivative of E sub r and multiply that by r. So here's the first part of the product rule and the second part of the product rule, and that would equal this here. So when we take the derivative, let's look at the first part of the product rule. Derivative of r with respect to time multiplied by the unit vector in the radial direction. That's going to be r dot, right? R dot E sub r. That's given us this. This r times the derivative of E sub r with respect to time, how we are changing this into r d theta, because this is staying the same. These two are staying the same. This is changing to r d theta dt times E sub theta. We're doing that by using these equations down here. E theta d theta dt equals d E sub r over dt. So this equation, we'll plug that in over here, and we get r d theta dt in the E theta direction. So that's r theta dot, right? D theta dt, that's just going to be theta dot. Dot is an indicator that we've taken the derivative with respect to time. So similarly, the particle acceleration vector is given by d dt. So let me once again mark in blue this time. Here is our, I want to make sure I mark the right thing, sorry. This is our velocity vector. So if we take the derivative of this velocity vector, or we could even, I think they did it with this one. Okay. If we take the derivative of our velocity vector right here with respect to time, that'll give us acceleration. So we're taking the derivative. This equation is just right here. We're taking the derivative of that with respect to time. So there's a lot of little tricks and stuff. I mean, here it's not even that complicated. We're doing the product rule again. So we have to take the derivative of this, multiply it by that, plus the derivative of this and multiply it by that. So d squared r over dt squared, basically the double derivative of r times this. So that's going to give us r dot, right? And then dr dt multiplied, now we're doing the second part of the product rule. And then this term is just going to be a triple product rule. So let's stick with this one first. The r double dot's pretty simple. And then we get dr dt multiplied by the derivative of er dt. And they kind of skip a step here because I believe we're going to exploit this rule again. And it because there's two, it'll be a double derivative of theta multiplied by r. And it's also a negative as well. So that's probably coming from this equation here. So minus r theta dot squared. Times, and this is for the radial component of direction. Now we do the triple product rule, d dt for this one. So we're going to apply the derivative to this term here. In order to do that, we're going to do a triple product rule. D, the derivative of r multiplied by these two terms, the derivative of this term multiplied by these two terms, and then the derivative of the unit normal vector in the theta direction multiplied by these two terms. And the first one is here. That's going to end up being an r theta dot, and then both of these end up being r dot theta dot, but there's two of them, so it ends up being 2 there. And you can utilize these equations to determine how they did that, like with this dr d theta dot dt, that is an r dot and a theta dot. We can see that pretty clearly, right? R dot, theta dot. So that's one of our r dot theta dots. This one is r double derivative of theta, so that's our r theta dot. And then this one is r times the derivative of theta times the derivative of this, which is just going to give us an r dot. Somehow we get an r dot here. This must be an r dot theta dot term coming from this, because this one gave us this one gave us a r dot theta dot, and this one gave us a r theta double dot, so that's this term. So this one must give us an r dot theta dot, and that's probably because, let's see, t equals negative er. Somehow from this, they get you an r dot theta dot, utilizing these equations here. So let's just get into some concepts to further illustrate this. If you are traveling in a perfect circle, what is always true about the radial and transverse coordinates and the normal tangential coordinates? Let's quickly draw some of these. This one here is the that would be the radial. This one here would be the normal. And this one here would be 2. Try to guess before I write it down. But it would be E sub t tangent. And it would also be E sub theta. And if we remember, the E sub q was perpendicular to E sub r. So I'm pretty sure the E sub q is in this direction. Unfortunately, they went with E sub q for being one of the answers here, but you don't really use E sub q that much. So when doing this on a perfect circle, we can see that our radial direction, our normal direction, tangential, and theta direction, the coordinate systems kind of line up. The only difference being that the radial unit normal is in the opposite direction of the unit normal for the normal direction. But the normal and tangential, the two coordinate systems are on the same lines, as you can see. And the tangent and the theta unit normal is in the same direction. It's even in the same direction and the same line. These are in the same line but opposite directions. So let's see which one of these would always be true. The E sub r direction is identical to the E sub n direction. So the radial direction is identical to the normal direction. This is almost true because they, but well, it's not. I guess you can't really say it's almost true. They're on the same line, but they're in opposite directions. So the direction isn't identical at all. It's the complete opposite, because this is our E sub r and this is our E sub n. So they're not in the same direction. The E sub r direction is not identical to the normal direction. The E sub q direction is perpendicular to the E sub n direction. So the E sub q is the opposite of E theta. That is perpendicular to the normal direction. That is true. E sub q is perpendicular to the normal direction. Let's see the last one. The E sub q direction is parallel to the E sub r direction. That is not true. The E sub q direction is perpendicular, and it's always perpendicular to the radial direction. And we could sub out E sub q for E sub t or E sub theta in these, and it would still be true for B. B is the correct answer, and if you put E theta here or ET, those are always going to be perpendicular to the normal direction when we're dealing with a perfect circle. The tangential, ET, E sub t, E sub theta, that's going to be perpendicular to our normal direction here, as is EQ. So the correct answer is B, and it is perpendicular there. Okay, so radial and transverse components. When a particle position is given in cylindrical coordinates, it is convenient to express the velocity and acceleration vectors using the unit vectors E capital R, E theta, and K, where the capital R is now still our radial direction, but now we're talking about cylindrical coordinates. E theta is it's very similar to what we just did with normal, tangential, and binormal. Only a little bit different, but this is the best way to expand these into three-dimensional components. So the position vector is just going to be R equals big R times E sub R, so that's this vector right here, plus Z times K. So that's not too complicated. Our K is our vertical direction. It is parallel to the Z axis. So a big thing with these problems is to just realize what we're doing, and what we're doing is coordinate transformations to make problems easier. So as confusing as maybe all this notation gets jumbled on here, if you zoom out a little bit, what are we doing? We're tracking particle P, and we're just applying coordinate transformations. So instead of X and Y plane, we have a radial and theta plane. It's almost like polar coordinates, but a little bit different because it's cylindrical. Velocity vector, V equals dr dt, and that's just going to be r dot E capital R, R theta dot plus Z dot K. So if you see this was the same as the previous radial transverse components that we saw on the previous slide. We're just adding in this Z dot K term to make it three-dimensional. And then the acceleration vector is going to be the same thing. This is what we just derived a few slides ago. It was a pretty complex derivation. And then we add on a Z double dot K to account for the change in the Z direction, or what we're referring to as the K direction, happens to be parallel to a Cartesian Z. And this is how we would expand this into 3 dimensions. Okay. So this is sample problem 11.18. We have a shaft with a collar on it, and it is rotating about point O. The distance between the collar to point O is given by R. The distance from the original, I guess you could refer to it as the 0 degree, to its current position is theta. This angle is given by theta. So this looks like a good problem to utilize our radial and transverse equations. The rotation of the arm about O is defined by theta equals 0.15 t squared, where theta is in radians and t in seconds. Collar B slides along the arm such that R equals 0.9 minus 0.12 t squared, where R is in meters. So here comes the question. We could write all of that stuff down. And now we'll look at the question. After the arm has rotated through 30 degrees, determine the total velocity of the collar, the total acceleration of the collar, and the relative acceleration of the collar with respect to the arm. Oh, so that last part might be a little bit tricky. The total velocity of the collar and the total acceleration of the collar shouldn't be too difficult as long as we utilize the formulas that were given to us on the previous slides. Here's the strategy, evaluate t for theta equals 30, evaluate the radial and angular positions and first and second derivatives at time t, calculate the velocity and acceleration in cylindrical coordinates, evaluate acceleration with respect to the arm. So first, a good approach to problems like this would be to go through it and get our theta dot, and our theta double dot, because those terms were all in our acceleration term. And we could do the same thing for r as well. We can do our r dot, and our r double dot. And if you're just methodical and organized with this type of problem, it shouldn't be too complicated. Theta equals 0.15 t squared, and 30 degrees equals 0.524 radians. So we do the radian conversion and then solve that. So 0.524 divided by 0.15, and then the square root, you end up getting t, you solve for t, 1.869 seconds. Now we can go through and get our r double dot, our r dot, r double dot, theta dot, theta double dot. You take the derivative of this, you're gonna the 0.9 drops out, you get 0.24 t, and you take the derivative of that, you're only gonna get minus 2.4. So r double dot is just minus 2.4. We have a term for t here, so we can plug in t, and now we have these three r terms. And now let's do the same thing for theta. We have 0.15 t squared. You can plug in t right there. You get 0.524. When we take the derivative of that, we bring the 2 down, multiply it, get 0.3 t, and then for the double derivative, you just get 0.3. So this is a good practice if you're going to go for this coordinate system. This is a good practice to utilize, and a good indicator that we're using this coordinate system. I mean, maybe problems won't always be this simple, but they literally give it to you in terms of an r and in terms of a theta, so that should say, hey, I think we're probably going to be using cylindrical coordinates for this problem. Okay, so now we can calculate the acceleration. The velocity in the radial and velocity in the theta direction are given by these two equations here. R dot equals the velocity in the radial direction. R theta dot equals the velocity in the theta direction. We just grab the terms from the previous slide. Our R dot, R double dot, we solved for all of these. So we're literally just plugging these terms in and getting the answer. Now to get the full velocity, again, we're using the square root of the two terms, add them together, and then take the square root of that. And in this case, I think earlier they didn't show it in terms of an inverse tangent, but to get the direction, you just take the inverse tangent of theta over r, and that will give you this angle beta shown here. So now we have the velocity vector, the magnitude, and the direction. And a lot of problems in dynamics are solved by getting the magnitude and the direction of a vector. So that's our velocity component. The next thing it asked for was the acceleration. So it's going to be the same thing. It's just a longer formula. It was the long r double dot minus r theta dot squared, and then this term has this in it. But we have all these values. This was a pretty simplistic problem and a pretty good example of how to use this. It's a pretty good example of showing you why doing coordinate transformations can be beneficial to solving certain problems. So we get our acceleration in the radial direction here. We get the acceleration in the theta direction here, and we're doing the same process. Acceleration equals the square root of the radial component squared plus the theta component squared, and in this case the angle is here, inverse tangent of the theta component over the radial component, and we have the magnitude and the direction of our acceleration vector. It looks like our velocity vector is headed this way, and the acceleration vector is heading that way. So the final one was the tricky component, and that was evaluate acceleration with respect to the arm. Motion of the collar with respect to the arm is rectilinear and defined by coordinate r. Coordinate r. Let me bring a few of these up. So we're taking the position of point O. Oh, so it's only taking the component in the radial direction, I believe, then. Yeah. And just neglecting the theta component, because if the motion, it says with respect to the arm, it would be better to me if it says with respect to the origin, because it seems like we're taking it with respect to the origin. This is the acceleration of the collar with respect to the origin. It is moving towards the origin. But we're actually taking it with respect to point A, I believe. So, if we reflect and think on this, you should consider polar coordinates for any kind of rotational motion. They turn this problem into a straightforward solution, whereas any other coordinate system would make the problem much more difficult. One way to make this problem harder would be to ask you to find the radius of curvature in addition to the velocity and acceleration. To do this, you would have to find the normal component of the acceleration, that is the component of acceleration that would be perpendicular to the tangential direction defined by the velocity vector. So let me read that again. One way to make this problem harder would be to ask you to find the radius of curvature in addition to the velocity and acceleration. So if you found the radius of curvature of this, then you would be able to utilize the normal and tangential components to solve this problem. But that would in fact make it harder, because it's a difficult calculation to calculate the radius of curvature. But if you did find the instantaneous radius of curvature, maybe it would be simpler than using this method. So that's why it's always difficult to determine how to approach each problem in dynamics. That's part of the challenge of the class. One, it's just an interesting class when getting a better understanding of motion and solving these problems, but also it's a great class for problem solving because there are often multiple ways to solve problems. And it says to do this, to find the instantaneous radius of curvature, you would have to find the normal component of acceleration. Okay, so they're not saying calculate the radius of curvature like there's some equation that would give us that. It's saying calculate the normal component of acceleration and the tangential component of acceleration, and then work backwards to get the radius of curvature. So that would be a complex problem. The component of acceleration that is perpendicular to the tangential direction defined by the velocity vector. So yeah, that would make the problem more complicated. It would be like working backwards from the normal and tangential components. Just like the problems we just solved, but almost in reverse. And I believe that is all for this lecture.